You know what question keeps me awake at night? Not in a bad way. In that good way where your mind just can't stop wondering. It's this: how big is the universe? And I don't mean that as a casual question. I mean, really, how big? Like, if you could hop in a spaceship and just keep going, where would you end up? What would you find? The answer is going to blow your mind, because it's not just big. It's not even just really big. It's so incomprehensibly vast that our brains literally didn't evolve to grasp it. But we're going to try anyway, because that's what we do. We're curious creatures. We look up at the night sky and we ask questions. Let me start with something you can actually visualize. Earth, our home. It's about 12,742 kilometers across. That's roughly 7,918 miles, if you prefer. Now, that seems big, right? You could spend your entire life traveling and never see every corner of it. There are people who've done exactly that. But here's where it gets interesting. Earth is tiny, absolutely minuscule compared to what's out there. The moon, our closest neighbor, is about 384,400 kilometers away. That's the distance light travels in 1.3 seconds. Light moving at 300,000 kilometers per second. Think about that for a moment. Light is the fastest thing in the universe. Nothing can move faster. And it still takes 1.3 seconds to get from Earth to the moon. Now let's zoom out a bit. The sun, that giant ball of burning plasma that gives us life, is about 150 million kilometers away from Earth. We call this distance an astronomical unit, or AU for short. Light from the sun takes about 8 minutes and 20 seconds to reach us, which means, and this is wild, when you look at the sun, you're not seeing it as it is now. You're seeing it as it was 8 minutes ago. If the sun suddenly vanished, winked out of existence, we wouldn't know for 8 minutes. We'd just keep going about our day, completely unaware. But the sun isn't going anywhere. It's going to be around for another 5 billion years or so. Plenty of time. Let me tell you about our cosmic neighborhood. The solar system, Neptune, the farthest planet from the sun, orbits at about 30 AU. That's 4.5 billion kilometers. Light from the sun takes about 4 hours to get there. But the solar system doesn't end at Neptune. Not even close. There's the Kuiper Belt, a region of icy bodies beyond Neptune. Pluto hangs out there. Then beyond that, way beyond that, there's the Oort cloud. The Oort cloud is this spherical shell of icy objects surrounding our entire solar system. It extends out to about 100,000 AU. That's nearly 2 light years. A light year, that's the distance light travels in 1 year. About 9.5 trillion kilometers. And the Oort cloud extends out to 2 of them. The solar system is huge, way bigger than most people think. But here's the thing. In cosmic terms, it's nothing. A speck, a grain of sand on an infinite beach. The nearest star to our sun is Proxima Centauri. It's 4.24 light years away. Light takes 4.24 years to travel from there to here. If you wanted to drive to Proxima Centauri at highway speed, say 100 kilometers per hour, it would take you about 46 million years. That's not a typo. 46 million years. Our fastest spacecraft, Voyager 1, launched in 1977, is currently traveling at about 17 kilometers per second. Relative to the Sunday, at that speed, it would take about 73,000 years to reach Proxima Centauri, if it were headed in that direction, which it's not. Space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. Douglas Adams said that, and he was absolutely right. Now, Proxima Centauri is just one star among hundreds of billions in our galaxy. The Milky Way is a barred spiral galaxy. It's got this beautiful spiral structure with arms reaching out from a central bar. We live in one of those arms. The Orion arm, about 26,000 light years from the galactic center. The Milky Way is about 100,000 light years across. Light takes 100,000 years to travel from one side to the other. Let that sink in for a moment. Our entire solar system, which we just established is incomprehensibly huge, is just a tiny dot in this galaxy. And light takes 100,000 years to cross it. And there are somewhere between 200 and 400 billion stars in the Milky Way, each one potentially with its own system of planets, its own story. When you look up at the night sky and see the Milky Way stretching across like a river of light, you're looking at billions of stars, billions of suns, each one mind-bogglingly far away. But here's where it gets truly wild. The Milky Way isn't alone. The nearest large galaxy to us is Andromeda. It's 2.5 million light years away. Light takes 2.5 million years to travel from Andromeda to us, which means when you look at Andromeda through a telescope, you're seeing it as it was 2.5 million years ago. Before humans existed, before our ancestors walked upright, you're literally looking back in time. Andromeda is bigger than the Milky Way, about 220,000 light years across. It contains about 1 trillion stars. That's 1,000 billion, a million millions. And in about 4.5 billion years, Andromeda and the Milky Way are going to collide. Not like a car crash, more like two ghosts passing through each other. The distances between stars are so vast that actual collisions are incredibly unlikely. But the gravitational dance will reshape both galaxies. They'll merge into one giant elliptical galaxy. Some people call it Milkomeda. I prefer that name. The sun will likely survive this collision. Might even get flung into a different part of the merged galaxy. Earth might survive too, though by that time, the sun will be so hot that Earth's oceans will have boiled away. Life on Earth will be long gone, unless we've moved elsewhere by then, which, honestly, we probably should. But I'm getting ahead of myself. Let's zoom out even more. The Milky Way and Andromeda are part of what we call the local group, a collection of about 54 galaxies bound together by gravity. Most of them are dwarf galaxies, small galaxies with only a few billion stars. But there are a few big ones: Milky Way, Andromeda, and the Triangulum Galaxy. The local group is about 10 million light years across. That's big. But it's just one small cluster in a much larger structure. The local group is part of the Virgo supercluster, a massive collection of galaxy groups and clusters spanning about 110 million light years. The Virgo cluster, at the heart of the supercluster, contains about 1,300 galaxies, maybe more. We're still counting. And our local group is on the outskirts of this supercluster. We're practically in the suburbs. But even the Virgo supercluster is just one piece of something larger, the Laniakea supercluster. Laniakea means immense heaven in Hawaiian. And it's aptly named. It contains about 100,000 galaxies spanning 520 million light years. We discovered Laniakea in 2014. We literally didn't know we were part of this structure until recently. That's how big and complex the universe is. And Laniakea isn't unique. There are countless other superclusters scattered throughout the observable universe. The observable universe. That's an important distinction. Let me explain. When we talk about the size of the universe, we're usually talking about the observable universe, the part we can actually see. And the reason we can't see beyond that isn't because our telescopes aren't good enough. It's because of the speed of light. Light takes time to travel, and the universe has only existed for a finite amount of time. About 13.8 billion years, give or take, which means light from objects farther than 13.8 billion light years away hasn't had time to reach us yet. It's still on its way. So there's a horizon, a cosmic horizon beyond which we can't see. Not because there's nothing there, but because the light hasn't reached us yet. But here's where it gets even more interesting. The observable universe isn't 13.8 billion light years in radius. It's much bigger. About 46.5 billion light years in radius, about 93 billion light years in diameter. Wait, what? How can we see light from objects farther than 13.8 billion light years if light has only been traveling for 13.8 billion years? The answer is expansion. The universe is expanding. Space itself is stretching. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us. But in the time it took that light to reach us, space expanded. The galaxy moved farther away. So now, today, that galaxy is about 46 billion light years away. Even though its light has only been traveling for 13 billion years. It's counterintuitive, I know, but that's how expansion works. It's not that galaxies are moving through space. It's that space itself is growing, stretching like the surface of an inflating balloon. Imagine dots on a balloon. As you inflate it, the dots move apart, not because they're moving on the surface, but because the surface itself is expanding. That's what's happening with galaxies. They're not flying through space. Space is expanding between them. And here's the kicker. The expansion is accelerating. Galaxies are moving away from each other faster and faster. We discovered this in 1998. It was so surprising, so unexpected, that the scientists who discovered it won the Nobel Prize. We call the force driving this acceleration dark energy, and we have no idea what it is. Dark energy makes up about 68% of the universe, the majority of everything that exists, and we don't know what it is. Dark matter, which we also don't really understand, makes up about 27%. Regular matter, the stuff we're made of, atoms and molecules, makes up only about 5%. We're living in a universe where 95% of it is made of stuff we don't understand. That's humbling and exciting because it means there's so much left to discover, so many mysteries waiting to be solved. But let's get back to size. The observable universe is 93 billion light years across. That's incomprehensibly vast. To put that in perspective, if you could shrink the sun to the size of a white blood cell and shrink the Milky Way using the same scale, the Milky Way would be the size of the continental United States. And on that scale, the observable universe would be, well, it would span the entire solar system, and then some. Our brains literally can't visualize these scales. We didn't evolve to think in billions of light years, but we can use math, we can use physics, we can extend our minds beyond their natural limits. And when we do, we discover something amazing. The universe is structured. It's not just a random scattering of galaxies. Galaxies are arranged in filaments and sheets surrounding vast empty voids. The cosmic web, we call it. These filaments are the largest structures in the universe. Some span hundreds of millions of light years. The voids, the empty spaces between, are equally vast. Some are 300 million light years across, nearly empty. Just a few stray galaxies here and there. This structure formed from tiny quantum fluctuations in the very early universe. During a period called inflation, these fluctuations got stretched to cosmic scales. Over billions of years, gravity amplified them. Matter flowed toward denser regions. Galaxies formed at the intersection. The structure we see today is the result of 13.8 billion years of evolution, of gravity sculpting the universe into this beautiful, intricate pattern. And we can see it with powerful telescopes and massive surveys. We can map this structure. We can see how galaxies are distributed across billions of light years. It's breathtaking, this cosmic architecture, this grand design. But here's a question that might blow your mind. Is the observable universe all there is? The answer is almost certainly no. The observable universe is just the part we can see. But the universe likely extends far beyond that. Probably infinitely, we don't know for sure. But the evidence suggests the universe is either infinite or so large that the difference doesn't matter. Measurements of the universe's curvature show it's flat, or very close to flat. And a flat universe that's expanding is likely infinite, which means there could be infinite galaxies, infinite stars, infinite planets, infinite possibilities. And if the universe is truly infinite, then somewhere out there, impossibly far away, there's another galaxy just like the Milky Way, another solar system just like ours, another Earth, another you reading these words, or not reading them, making different choices. In an infinite universe, everything that's possible happens, not just once, infinitely many times. It's called the ergodic principle, and it's mind-bending. But even if the universe is infinite, there's another layer to this. The multiverse. The multiverse is the idea that our universe, everything we can observe, is just one of many universes. Maybe infinitely many. These other universes would be causally disconnected from ours. We could never observe them, never visit them, never communicate with them. They'd be separate realities, each with their own laws of physics, their own constants of nature, their own histories. This isn't science fiction. It's a serious scientific hypothesis. It emerges naturally from certain theories in cosmology and quantum mechanics. Inflation, that period of rapid expansion in the early universe, might not have stopped everywhere at once. It might still be going on in some region, creating bubble universes. Each bubble a separate universe with its own Big Bang, its own space and time. Eternal inflation, they call it. And if it's correct, there are infinitely many universes being created all the time. Then there's the many worlds interpretation of quantum mechanics. The idea that every quantum measurement causes the universe to split into multiple branches, each branch representing a different possible outcome. In this view, there are countless parallel universes, constantly branching, creating new realities with every quantum event. And string theory suggests the possibility of other dimensions, extra spatial dimensions beyond the three we experience. These dimensions might be curled up, too small to detect, or they might be large but somehow hidden from us. If there are extra dimensions, there could be other universes existing alongside ours in higher dimensional space. Brain worlds, they're called. Universes as membranes floating in higher dimensional space. These ideas are speculative. We don't have direct evidence for the multiverse, but they emerge from our best theories. And if they're correct, then the question, how big is the universe, becomes almost meaningless. Because there wouldn't be just one universe. There'd be infinitely many, each potentially infinite in size. The totality of reality would be beyond comprehension, beyond anything we could measure or map. But let's come back to what we can actually observe. The 9.3 billion light-year diameter sphere that is the observable universe. How many galaxies are in that volume? The best estimates suggest about 2 trillion galaxies. That's 2,000 billion. Each one with billions or even trillions of stars. Let's do some math. If the average galaxy has 100 billion stars, then the observable universe contains about 200 billion trillion stars. That's 200 sextillion. Written out, that's 200 sextillion stars. And many of those stars have planets. Based on observations from the Kepler Space Telescope, we think most stars have at least one planet, which means there are probably more planets in the observable universe than there are stars. Hundreds of sextillions of planets, and some fraction of those planets are rocky, Earth-like, in the habitable zone where liquid water can exist. How many? We don't know exactly. But estimates suggest maybe 20% of sun-like stars have an Earth-like planet in the habitable zone. That's still billions of potentially habitable planets just in the Milky Way, and hundreds of billions or trillions across the observable universe. The question isn't whether life exists elsewhere. The question is how common it is and whether we'll ever be able to detect it. The distances are so vast, the timescales so long. It's entirely possible that civilizations exist, have existed, will exist, but we'll never know about them. Ships passing in the cosmic night, never close enough in space or time to make contact. Unless, of course, faster than light travel is possible. Or some other method of spanning these impossible distances. Wormholes, warp drives, technologies we can barely imagine. The laws of physics as we understand them don't forbid these things outright. They're just extraordinarily difficult, requiring exotic matter or energies we can't currently produce. But maybe someday, maybe 1 million years from now, maybe 1 billion, if humanity survives that long, if we spread beyond Earth, beyond the solar system, into the galaxy, we could become a spacefaring civilization, exploring the Milky Way, building homes among the stars. It's a beautiful dream, and nothing in physics says it's impossible. But let's talk about something else. The age of the universe and how we know it. We said the universe is 13.8 billion years old. How do we know that? It comes from multiple lines of evidence. But the most direct comes from the cosmic microwave background, the CMB. The CMB is light from the early universe, about 380,000 years after the Big Bang. Before that, the universe was too hot and dense for light to travel freely. It was a plasma, electrons and protons flying around, constantly absorbing and emitting photons. But as the universe expanded and cooled, it reached a temperature where electrons and protons could combine to form hydrogen atoms. Suddenly, light could travel freely, and that light has been traveling ever since. For 13.8 billion years, we can see it today. Faint microwave radiation coming from every direction in the sky. It's incredibly uniform. The same temperature in every direction to better than 1 part in 100,000, but not perfectly uniform. There are tiny variations, hot spots and cold spots, fluctuations of 1 part in 100,000. Those fluctuations are the seeds of structure, the regions that would eventually become galaxy clusters, the denser patches where gravity pulled matter together. By studying the CMB in detail, measuring the pattern of hot and cold spots, we can determine the age of the universe, its composition, its geometry. And we get 13.8 billion years, give or take about 20 million years. That's a pretty precise measurement. We can also measure the universe's age by looking at the oldest stars. Globular clusters contain some of the universe's oldest stars. By studying their properties, we can estimate their age. And we get about 12 to 13 billion years. consistent with the CMB measure. Another method looks at the expansion rate of the universe, the Hubble constant. By measuring how fast galaxies are moving away from us and how far away they are, we can extrapolate backward and calculate when everything was together. When we do that, we get about 13.8 billion years. Again, consistent. Multiple independent lines of evidence all pointing to the same answer. That's how we know. That's how science works. Not just one measurement, but many, all corroborating each other. Now, 13.8 billion years is a long time, but it's finite. The universe had a beginning. Before the Big Bang, there was, well, we don't know. Maybe nothing. Maybe something else. Maybe time itself didn't exist yet. General relativity breaks down at the Big Bang. The equations give infinities, singularities, which is physics' way of saying, I don't know what's going on here. We need a theory of quantum gravity to understand what happened at time zero, and we don't have one yet. String theory might be it, loop quantum gravity might be it, something else might be it. But until we can test these theories, until we have experimental evidence, we're just speculating. What we do know is that the universe was once incredibly hot and dense, and it's been expanding and cooling ever since. In the first fraction of a second, extraordinary things happened. Particles that don't exist anymore were common. Forces that are now separate were unified. It's like running time backward and watching ice melt into water. Water evaporate into steam. Steam break down into hydrogen and oxygen. Atoms break apart into electrons and nuclei. Keep going back and you get to a point where even protons and neutrons break down into quarks and gluons, where the electromagnetic and weak forces merge into the electroweak force. Further back still, maybe all four fundamental forces were unified. Gravity, electromagnetism, strong and weak nuclear forces. All aspects of one superforce. That's the dream, the theory of everything. Understanding how all forces arise from one unified framework. We're not there yet, but we're working on it every day in laboratories and universities around the world. Physicists are smashing particles together at incredible energies, trying to recreate conditions from the early universe, trying to see what happens. Astronomers are building bigger telescopes, looking farther into space, and therefore farther back in time. The James Webb Space Telescope, launched in 2021, can see galaxies that formed when the universe was only a few 100 million years old. We're seeing the universe's infancy, watching the first stars ignite, the first galaxies assemble. It's incredible. We're living in a golden age of cosmology, learning things about the universe that people a century ago couldn't have imagined. And every answer raises new questions. That's the beauty of science. The more we learn, the more we realize we don't know. But let's talk about expansion again, because it's crucial to understanding the universe's size and fate. The universe is expanding. We've established that. But what does that mean for the future? If expansion continues forever, and it seems like it will, then galaxies will keep moving apart. The universe will keep getting bigger. Eventually, billions of years from now, galaxies outside our local group will be so far away that we can't see them anymore. Not because they're too faint, but because space is expanding faster than light can cross it. They'll be beyond our cosmic horizon, causally disconnected from us. Future astronomers, if they exist, will look out and see only the local group, maybe just the merged Milkomeda galaxy. They'll have no idea that there are trillions of other galaxies out there. The expansion will have hidden them. All the evidence we have today for the Big Bang, for expansion, for dark energy, it might not be visible to them. They might think the universe is just one galaxy surrounded by empty space. It's sobering to think about. What we can see and learn is contingent on when we exist, on the cosmic era we inhabit. We're lucky to live when we do. When the universe is still young enough, still transparent enough, that we can see its history. But expansion also means that eventually, in trillions of years, stars will stop forming. All the hydrogen gas will be used up. Existing stars will die. The universe will grow dark and cold. Black holes will be the last remnants of structure. And even they will evaporate eventually, Hawking radiation slowly eating away at them over unimaginable timescales. 10 circumflex 100 years or more. That's a 1 followed by 100 zeros. A Google years, after that, the universe will be empty, just particles occasionally interacting across vast distances. Nothing interesting happening anymore. The heat death of the universe. Maximum entropy. No gradients, no structure, no complexity. It's a bleak future. but it's also so far away that it's almost abstract. The sun won't die for another 5 billion years. The Milky Way Andromeda collision is 4.5 billion years away. Humanity, if we survive, has eons to explore, to build, to discover, to create meaning in an indifferent universe. And who knows what we'll learn in that time? What technologies we'll develop, what understanding we'll achieve. Maybe we'll figure out how to survive the heat death, how to create pocket universes with lower entropy, how to transcend the limitations we see today. Or maybe we'll discover that our understanding is wrong, that the universe has surprises waiting, that the future is different from what we predict. Science is always provisional, always open to revision. That's its strength. Let me tell you about something mind-blowing. The Planck scale, at the smallest scales, around 10 circumflex negative 35 meters and 10 circumflex negative 43 seconds, quantum effects and gravity become equally important. Space and time themselves might become grainy, discrete, made up of tiny indivisible units. At these scales, our classical notions of space and time break down. Space might not be continuous, but quantized. Time might not flow smoothly, but tick in discrete steps. This is the realm of quantum gravity, where we need a theory that merges quantum mechanics and general relativity. And here's the wild part. If space is quantized, if there's a minimum unit of distance, then in a sense the universe is digital, made up of discrete bits, like pixels on a screen. At large scales, it looks smooth and continuous. But zoom in far enough, and you see the individual units. Some physicists think the universe might literally be a computational structure, information processing at the most fundamental level. The holographic principle goes even further. It suggests that all the information in a volume of space can be encoded on the surface of that volume, like a hologram, a 2D surface encoding 3D information. If that's true, then our 3D universe might be a projection from a 2D boundary. Reality as we experience it might be holographic. It sounds like science fiction, but it's serious theoretical physics. Emerging from studies of black holes and string theory, what does this mean for the size of the universe? Well, if the holographic principle is correct, then the information content of the universe is finite, even if space extends infinitely, because information is encoded on boundaries, and boundaries grow with area, not volume. An infinite universe would have infinite boundary, and therefore infinite information. But the information density would be finite. It's subtle. And we're still figuring out what it all means. But the point is, when you ask, how big is the universe? You're not just asking about distance. You're asking about information, about structure, about the fundamental nature of reality. And the answers are strange and beautiful and deeply counterintuitive. Let me bring this back to something personal, something human. We're talking about scales that are so vast, timescales so long, that they feel abstract, meaningless almost, but they're not, because we're part of this universe. We're made of atoms forged in stars billions of years ago. The iron in your blood was created in a supernova. The calcium in your bones came from dying stars. You are literally stardust. Not metaphorically, literally. Every atom in your body, except for hydrogen, was created in nuclear reactions inside stars or during supernova explosions. Those stars lived and died billions of years ago. Their material spread through space, eventually condensing into new stars, new planets. Our solar system formed from that enriched material 4.6 billion years ago. Life emerged on Earth about 3.8 billion years ago. Simple, single-celled organisms at first. For billions of years, that's all there was. Bacteria, archaea. Simple life doing simple things. But eventually, about 600 million years ago, complex life exploded. Animals, plants, fungi, evolutionary arms races, predator and prey, competition and cooperation. Intelligence emerged, not just in humans, in dolphins, in elephants, in octopuses, in crows, but human developed something unique: language, culture, science. The ability to ask questions about the universe, to build telescopes, to do math, to figure out how big everything is. We're the universe's way of knowing itself, of understanding itself. Carl Sagan said that. And it's true. For billions of years, the universe existed without knowing it existed. Stars formed and died. Galaxies collided. Black holes grew, but nobody was watching. Nobody was asking why. Then, on at least one small rocky planet orbiting an average star in an unremarkable galaxy, matter organized itself into forms capable of thought, capable of wonder, capable of science. And now the universe can look at itself, can measure itself, can ask, how big am I? That's extraordinary. That's what makes us special. Not that we're at the center. We're not. We're in the suburbs of the suburbs, insignificant in spatial terms. But we can understand, we can know, we can appreciate the vastness and beauty of it all. And that understanding doesn't diminish us. It elevates us. Yes, we're tiny compared to the universe, a dust mote in a cosmic ocean. But we're also complex, sophisticated. We contain multitudes. There are more neural connections in your brain than there are stars in the Milky Way. About 100 billion neurons, each connected to thousands of others. Your brain is the most complex structure we know of in the universe. And you have one. You are one. So when you ask how big is the universe, remember that size isn't everything. Complexity matters. Information matters. Consciousness matters. The universe is vast. 93 billion light years in diameter in its observable portion, possibly infinite beyond that. But it took 13.8 billion years to produce something as intricate and amazing as you. That's worth something. That means something. We're not just passengers in this universe. We're participants. We're part of the story. Every time you look up at the night sky and feel that sense of awe, that's the universe experiencing itself. Every time a scientist makes a discovery, solves a problem, that's the universe learning about itself. Every time an artist creates something beautiful, that's the universe expressing itself. We're not separate from the cosmos. We're woven into its fabric, made from its substance, animated by its energy. The atoms in your left hand came from different stars than the atoms in your right hand. You're a collection of stellar debris, and that's not depressing. That's beautiful. You're a way for the universe to exist in concentrated, organized form, to experience itself, to know itself. So how big is the universe? Big enough to contain stars beyond counting, galaxies beyond number, possibilities beyond imagination, but also small enough, local enough, connected enough that you can understand it. You can be part of it. You can matter. The observable universe is 93 billion light years across, contains 2 trillion galaxies, 200 sextillion stars, countless planets. It's 13.8 billion years old. Expanding, accelerating, cooling. It began as a hot, dense state, the Big Bang, and has been evolving ever since. In the far future, it will grow cold and empty, but that's trillions of years away. For now, it's alive, dynamic, full of wonder, and we're here to see it, to study it, to appreciate it. That's the answer to how big is the universe. It's as big as it needs to be to create you, to create us, to create minds capable of asking the question. And that's pretty damn big, but not so big that we can't understand it, not so vast that we can't map it, not so complex that we can't appreciate its beauty. We're living in a golden age. We know more about the universe now than at any point in human history, and we're just getting started. There's so much more to learn. So many mysteries waiting: dark matter, dark energy, the nature of space and time, quantum gravity, the multiverse. These aren't just academic questions. They're invitations. Invitations to explore, to discover, to wonder. The universe is big, incomprehensibly big. But your capacity to understand it, to appreciate it, to find meaning in it, that's big too. Never forget that. You're part of something vast and ancient and ongoing. You're made of stars. You're animated by the same forces that govern galaxies. You're connected to everything through the fundamental laws of physics. And you can know this, you can understand this, you can feel awe at this. That's what makes the universe big. Not just its spatial extent, but its capacity to create complexity, to generate consciousness, to produce beings capable of asking, how big are you? And the universe answers through our telescopes and equations and observations, big enough to contain wonders beyond counting, big enough to surprise us, big enough to inspire us, but not so big that you don't matter, not so vast that your existence is meaningless. You're part of the story, a crucial part, the part that knows the story exists. So when you look up tonight, when you see those distant stars, remember, they're your ancestors in a real sense. They made the material you're composed of. They made the planet you stand on. They made the solar system that shelters you. And you, in turn, are the universe looking back at itself, understanding itself, appreciating its own magnitude. That's beautiful. That's profound. That's what it means to ask, how big is the universe? The answer is, it's as big as your mind can stretch to comprehend. And always a little bit bigger than that. Always with more to discover, more to learn, more to wonder at. And that's exactly how it should be. Good night, look up, and remember, you're part of something incomprehensibly vast and beautiful. Sleep well, knowing that the universe, in all its immensity, somehow produced you. And that's extraordinary. Let me tell you something else that absolutely fascinates me about the universe's size. It's about perspective, about scale. We've talked about light years and billions of galaxies. But let me give you another way to think about this. If you took the entire history of the universe, all 13.8 billion years, and compressed it into a single calendar year, here's what you'd get. January 1st at midnight, that's the Big Bang. The universe begins. For most of January, nothing much happens. Just energy cooling, particles forming, the first atoms coming together. The first stars don't ignite until about January 13th. Galaxies start forming around January 20th. The Milky Way forms sometime in February, still early in the cosmic year. Our solar system, that doesn't form until September 2nd, late in the year. The universe is already ancient by this point. Life on Earth emerges around September 21st. Simple, single-celled life. But life nonetheless. Complex life, animals and plants, they don't show up until December 17th. That's how long it took. Most of the year gone by. Dinosaurs rule the Earth from about December 25th to December 30th. Just a few days in cosmic terms. And humans, modern humans, we appear at 11:52 p.m. on December 31st, 8 minutes before midnight. All of recorded human history, from the first cities to right now, happens in the last 14 seconds of the year. Your entire lifetime? A fraction of a second. A blink. That's the scale we're dealing with. That's how big the universe is in time. And yet, in those last few seconds, we've figured all this out. We've measured the universe. We've traced our origins back to the Big Bang. We've looked out 13 billion light years. We've weighed galaxies. We've detected gravitational waves from black holes colliding billions of years ago. In the cosmic calendar, we just showed up. We're brand new, and we're already understanding how everything works. That's remarkable. That shows you the power of intelligence, of curiosity, of science. Now let me talk about something called the cosmological horizon, because it's crucial to understanding what we mean by the observable universe. The universe is expanding, and that expansion is accelerating. Galaxies far enough away are receding from us faster than light, not moving through space faster than light. That's impossible. But space itself is expanding fast enough that the distance between us grows faster than light can cross it. These galaxies are beyond our cosmological horizon. We'll never be able to see them, never be able to visit them, never be able to communicate with them. They're causally disconnected from us. In a very real sense, they're not part of our universe anymore. As time goes on, more and more galaxies will cross this horizon. They'll fade from view, redshifted into invisibility. Eventually, in hundreds of billions of years, only our local group will remain visible. Everything else will be gone. Future civilizations, if they exist, will have a very different view of the universe than we do. A much emptier view. They might not even realize the universe had a beginning, or that it's expanding. The evidence will have vanished beyond the horizon. We're lucky. We exist at a time when the universe is still young enough, still visible enough, that we can study its history. We can see the cosmic microwave background. We can observe distant galaxies as they were billions of years ago. We can piece together the story. That opportunity won't last forever. In cosmic terms, it's already closing. So we should make the most of it. We should learn everything we can while we can. Because the universe is showing us its secrets. And the window for seeing them clearly is finite. Let me tell you about redshift, because it's fundamental to how we measure distances in the universe. When an object moves away from you, the light it emits gets stretched. The wavelengths become longer, shift toward the red end of the spectrum. This is the Doppler effect. You hear it with sound too. An ambulance siren sounds higher pitched as it approaches, lower pitched as it recedes. Same principle with light. Approaching objects are blue shifted, Receding objects are redshifted. In an expanding universe, almost everything is redshifted because almost everything is moving away from us. The faster it's receding, the more redshifted it appears. Edwin Hubble discovered this in 1929. He measured the redshifts of galaxies and found they correlated with distance. Farther galaxies were more redshifted, which meant they were receding faster, which meant the universe was expanding. It was a revolutionary discovery. Before Hubble, most people thought the universe was static, unchanging, eternal. Einstein even added a term to his equations, the cosmological constant, to keep the universe static. He called it his biggest blunder after Hubble's discovery. Though, ironically, the cosmological constant came back. We now think it represents dark energy. So Einstein wasn't entirely wrong after all. But redshift gives us a way to measure cosmic distances. If we know how fast something is receding, we can calculate how far away it is. The most distant objects we've observed have redshifts of about 11 or 12. That means their light has been stretched by a factor of 11 or 12. They're so far away that they appear as they were just a few hundred million years after the Big Bang. We're literally looking back in time, seeing the universe's infancy. The James Webb Space Telescope is designed to see even farther, to observe the very first galaxies, the first stars, objects with redshifts of 20 or more, from when the universe was less than 200 million years old. These observations will tell us how structure formed, how galaxies assembled, how stars ignited. They'll fill in the gaps in our understanding, answer questions we've been asking for decades, and probably raise new questions we haven't thought of yet. That's how science works. Every answer is a doorway to more questions. Now, let's talk about cosmic inflation, because it's crucial to understanding why the universe is so big and so smooth. In the first fraction of a second after the Big Bang, the universe underwent exponential expansion, inflation. Space expanded faster than light, much faster. The universe doubled in size at least 60 times in less than 10 circumflex negative 32 seconds. A region smaller than an atom became larger than the observable universe today. Why did this happen? We think it was driven by a field, the inflaton field, like the Higgs field, but different. This field had energy, and in the early universe's extreme conditions, that energy caused space to expand exponentially. When inflation ended, the field's energy converted into matter and radiation, the hot, dense state we call the Big Bang. Inflation solves several problems. It explains why the universe is so flat, so uniform, so smooth on large scale. Without inflation, the universe shouldn't look the way it does. Different regions shouldn't have the same temperature, the same properties, because they wouldn't have had time to communicate, to equilibrate. But if everything started much closer together in a tiny region and then got inflated to cosmic scales, that explains it. Everything was in contact initially, then got stretched apart faster than light could keep them connected. Inflation also explains the tiny fluctuations we see in the cosmic microwave background. Those hot and cold spots, they came from quantum fluctuations in the inflaton field. Tiny random variations that got amplified to cosmic scales during inflation. Those fluctuations seeded structure formation. They became the galaxies and galaxy clusters we see today. So the structure of the universe on the largest scales came from quantum randomness on the smallest scales. Amplified by inflation. It's beautiful, it's elegant, and it's supported by observations. The pattern of fluctuations in the CMB matches the predictions of inflation almost perfect. But here's something wild. If inflation happened once, it probably happened many times. Maybe it's still happening. In regions far beyond our observable universe, inflation might still be going on, creating new space, new universes even. Eternal inflation, they call it. The idea that inflation never completely ends. It stops in some places, creating bubble universes, but continues in others. Each bubble would be causally disconnected, a separate universe with its own Big Bang, its own space and time. And if this is true, the multiverse isn't just possible, it's inevitable. There would be infinitely many universes, each potentially with different physics, different constants, different laws. Most would be sterile, unable to support life. But some, like ours, would have the right condition. And that's where observers like us would find ourselves. Not because we're special, but because we couldn't exist in the other universes. It's called the anthropic principle, and it's controversial. Some physicists love it, others hate it, because it's not really a prediction, it's an explanation for why things are the way they are, but it doesn't tell us what they should be. Still, if eternal inflation is real, the multiverse might be real too. And the question, how big is the universe, becomes, which universe are you asking about? Our observable universe is 93 billion light years across. But the full extent of our universe, beyond what we can see, might be infinite. And if there are other universes, the totality of reality is, well, it's beyond comprehension. Infinitely many infinities, each one a separate cosmos. Our brains aren't equipped to grasp that. But mathematically, it's consistent. It's possible. Let me tell you about the cosmic microwave background in more detail, because it's one of the most important discoveries in cosmology. In 1964, Arno Penzias and Robert Wilson were testing a radio antenna in New Jersey. They kept detecting noise, a faint hiss coming from every direction in the sky. They thought it was bird droppings. Pigeons had nested in the antenna. They cleaned it out. The noise persisted. They thought it was interference from New York City. They pointed the antenna away from the city. The noise persisted. No matter where they looked, no matter what they did, the noise was there. Uniform, unchanging, about 3 degrees above absolute zero. They didn't know it, but they discovered the cosmic microwave background, the afterglow of the Big Bang. This was light from 380,000 years after the Big Bang, when the universe first became transparent, when electrons and protons combined to form hydrogen. Before that, the universe was opaque, a plasma. Light couldn't travel freely. But after recombination, light could travel. And it's been traveling ever since. As the universe expanded, that light got stretched, redshifted. What was once visible light became infrared, then microwave. Today we see it as faint microwave radiation, about 2.7 Kelvin above absolute zero. And it's incredibly uniform. The same temperature in every direction to 1 part in 100,000, but not perfectly uniform. There are tiny variations, and those variations are crucial. They tell us about the universe's composition, its age, its geometry, its future. Missions like COBE, WMAP, and Planck have mapped the CMB in exquisite detail, measured those tiny variations with incredible precision. And what we've learned is extraordinary. The universe is flat, or very close to flat, which means it extends infinitely, or close to it. It's 13.8 billion years old, give or take 20 million years. It's made of about 5% ordinary matter, 27% dark matter, and 68% dark energy. The Hubble constant, the expansion rate, is about 67 to 73 kilometers per second per megaparsec. There's some disagreement on the exact value, which is actually a fascinating problem. But the point is, from studying the CMB, we've learned the universe's vital statistics. It's cosmic DNA, and it all matches our theoretical models. The Big Bang, inflation, structure, formation, it all fits together. That's not something we could have predicted. It's not obvious, but it's what observations show. The universe makes sense. It follows rules, rules we can understand. That's extraordinary. That's what makes science possible. Now let me talk about dark matter, because it's crucial to structure formation and the universe's evolution. We can't see dark matter. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. So how do we know it exists? Gravity. We see its gravitational effects. Galaxies rotate faster than they should based on visible matter alone. There must be more mass there. Dark matter provides it. Galaxy clusters contain more mass than we can account for from stars and gas. Dark matter fills the gap. Gravitational lensing, where massive objects bend light, shows there's more mass than we can see. Dark matter again, and the cosmic microwave background's pattern of fluctuations requires dark matter to form. Without it, the pattern would look different. So we know dark matter exists. We know how much of it there is, about 27% of the universe's total energy, but we don't know what it is. The leading candidate is WIMPs, weakly interacting massive particles, hypothetical particles that interact through gravity and maybe the weak nuclear force, but nothing else. We've built detectors to look for WIMPs, deep underground, shielded from cosmic rays, waiting for a WIMP to collide with ordinary matter. So far, nothing definitive, some controversial possible detections, but nothing confirmed. Maybe WIMPs are lighter or heavier than we thought. Maybe they interact even more weakly than expected. Maybe there's something else entirely. Actions are another candidate. very light particles that could be produced in huge numbers in the early universe. Or maybe dark matter isn't particles at all. Maybe it's primordial black holes. Small black holes formed in the early universe from density fluctuations. We don't know, but we're looking, and eventually we'll figure it out, because dark matter is out there, forming the scaffolding of cosmic structure, pulling galaxies together, shaping the universe's evolution. Without dark matter, galaxies wouldn't form the way they do, structure wouldn't look the way it does. We might not be here. So understanding dark matter is crucial to understanding the universe. And ourselves, dark energy is even more mysterious. We know even less about it. All we know is that it's causing the universe's expansion to accelerate. Galaxies are moving apart faster and faster. This was discovered in 1998. Two teams independently measured distant supernovae, type Ia supernovae, which are standard candles. They have a known luminosity. So by measuring how bright they appear, we can calculate how far away they are. And what they found shocked everyone. Distant supernovae were dimmer than expected, farther away than they should be, which meant the expansion had accelerated. Space had grown more than predicted. Something was pushing galaxies apart, some form of energy permeating space. Dark energy. The simplest explanation is the cosmological constant, Einstein's old fudge factor, a property of space itself. Every cubic meter of space has a certain amount of energy, and as space expands, more energy appears because there's more space. This energy has negative pressure. It pushes outward, causing acceleration. But why does the cosmological constant have the value it does? We don't know. Calculations suggest it should be much, much larger. 10 circumflex 120 times larger. That's the vacuum catastrophe. The worst prediction in physics. Clearly we're missing something fundamental. Some mechanism that cancels most of the vacuum energy but leaves a tiny residue. Or maybe dark energy isn't constant. Maybe it's a field that changes over time. Quintessence? If that's true, we might be able to detect the change. See, dark energy evolve. Missions are being planned to study dark energy in detail, to measure the expansion rate at different times in cosmic history, to see if it's constant or changing, because understanding dark energy is crucial. It determines the universe's fate. If dark energy stays constant, the universe will keep expanding forever, accelerating forever, eventually tearing itself apart in a big rip, or maybe not. Maybe the acceleration will level off. The universe will just expand forever at increasing speed, but not catastrophically. If dark energy weakens over time, the expansion might slow, maybe even reverse, leading to a big crunch. We don't know. We're watching, measuring, learning. The universe's fate is being written right now, and we're trying to read it. Let me talk about the shape of the universe, its geometry, because it's not what you might think. When we say the universe is flat, we don't mean it's like a pancake. We mean its geometry is Euclidean. Parallel lines never meet. The angles of a triangle add up to 180 degrees. The Pythagorean theorem works. But the universe could have been curved, positively curved like the surface of a sphere, or negatively curved like a saddle. In a positively curved universe, parallel lines eventually meet. Triangles have angles summing to more than 180 degrees. The universe is finite but unbounded, like the surface of a sphere. You can travel forever without hitting an edge, but you'll eventually come back to where you started. In a negatively curved universe, parallel lines diverge. Triangles have angles summing to less than 180 degrees. The universe is infinite, like a saddle shape extending forever. So which is it? Measurements of the CMB tell us the universe is flat, or so close to flat that we can't measure the difference, which means it's either exactly flat or has a curvature radius much larger than the observable universe. If it's exactly flat, it's infinite, extending forever in all directions. If it has slight curvature, it might be finite but enormous, wrapping around on itself on scales much larger than we can see. We don't know which. But either way, the universe is much, much bigger than the part we can observe. The observable universe is just a bubble, 93 billion light years across. But the full universe extends far beyond that. How far? We don't know. Maybe infinitely far. And if it's infinite, that has profound implications. Philosophical implications? In an infinite universe, every possible configuration of matter exists somewhere, not just once, infinitely many times. There are infinitely many copies of you making the same choices, and infinitely many making different choices. There are infinitely many Earths, infinitely many solar systems, infinitely many galaxies, just like the Milky Way. It's called the Copernican principle taken to its extreme. We're not special, we're typical. And in an infinite universe, typical means infinitely common. It's mind-bending. It challenges our sense of uniqueness, our sense of importance, but it's also beautiful in a way. You're not alone, you're not unique, but you're part of something infinite, something that contains every possibility, every dream, every fear, every hope. Somewhere, it's real. Let me bring this back to Earth for a moment, to something tangible. We've been talking about scales so vast they're abstract. Billions of light years, trillions of galaxies, infinite universes. But all of this started from something incredibly small, quantum fluctuations, tiny random variations in fields. The universe began as a quantum event, a fluctuation in the vacuum. Or maybe it didn't begin at all. Maybe it's eternal. But the part we can see, our observable universe, it emerged from something smaller than an atom. During inflation, that tiny region expanded to cosmic scales. The quantum fluctuations got stretched, amplified. They became the seeds of galaxies, of stars, of planets, of us. You are, in a very real sense, the descendant of a quantum fluctuation, a random blip in a field billions of years ago. That blip got amplified, became a density fluctuation. Gravity pulled matter into it. A galaxy formed, stars ignited, planets coalesced. On one of those planets, chemistry became biology. Life emerged, evolved, became complex, became conscious. And here you are, asking how big the universe is. It's an unbroken chain, from quantum uncertainty to conscious awareness, from the smallest scales to the largest. And you're part of it. You're the universe's way of experiencing itself. That's not poetic language, that's literal truth. You're made of atoms that were once inside stars. Your consciousness is a product of physical processes. You're the universe, localized, concentrated, aware. And when you look out at the night sky, when you feel awe at the vastness, that's the universe marveling at itself. It's self-reference, self-awareness on cosmic scales. You are small, tiny, insignificant in size, but you're also complex, sophisticated, rare, possibly. The universe is big, but it took 13.8 billion years to make you. That's not nothing. Every star that lived and died, every supernova that scattered heavy elements, every cosmic event that shaped the Milky Way, it all led to you. You're the product of cosmic evolution, the latest chapter in a story that began with the Big Bang. And you can understand this. You can know your own origins. Trace your lineage back to the beginning of time. That's extraordinary. That's what makes consciousness valuable, what makes intelligence precious. We're not just witnesses, we're participants. We're the universe understanding itself. And that understanding has value. Meaning, purpose, even if you want to use that word, not purpose imposed from outside, but purpose we create by asking questions, by seeking answers, by wondering. The universe is 93 billion light years across in its observable extent, possibly infinite beyond that, maybe part of an infinite multiverse. It contains 2 trillion galaxies, 200 sextillion stars, more planets than we can count. It's 13.8 billion years old, expanding, accelerating, evolving. It's made mostly of things we don't understand. Dark matter, dark energy, maybe more, but we're learning every day with every observation, every experiment, every calculation. We're figuring it out, piece by piece, mystery by mystery. And the more we learn, the more we realize how much we don't know. The horizon of knowledge keeps expanding, but that's okay. That's good, actually. It means there's always more to discover, more to wonder. The universe is big, bigger than we can fully comprehend, but we can try. We can stretch our minds, use mathematics, use physics, use our evolved capacity for abstract thought. And when we do, we find something beautiful, something elegant, something that makes sense, at least partially. The universe follows rules, laws, patterns we can understand. And those patterns tell a story. The story of how everything came to be, how it evolved, where it's going. We're part of that story, a crucial part, the part that knows the story exists. That's what it means to ask, how big is the universe? It's not just about distance or time or scale. It's about understanding our place in the cosmos, understanding what we are, where we came from, what we might become. And the answer is profound, humbling, inspiring. The universe is vast beyond imagining, ancient beyond comprehension, complex beyond belief, but it's knowable, at least partially. And that makes all the difference. So sleep well tonight. Rest easy knowing you're part of something magnificent, something that started as a quantum blip and became galaxies, stars, planets, life, consciousness, you. The universe is big, but you're part of it, connected to it, made from it. You know, there's one more thing I want to tell you before you drift off, something that ties all of this together in a way that still gives me chills every time I think about it. We've talked about the observable universe, that 9.3 billion light-year bubble we can see. But let me tell you about the particle horizon versus the event horizon of the universe. Because they're different things, and understanding the difference changes how you think about cosmic scale. The particle horizon is the farthest distance from which light has had time to reach us since the Big Bang. That's what defines our observable universe. Everything within 46.5 billion light years in any direction. But the event horizon is different. It's the farthest distance we could ever reach, even if we left right now traveling at the speed of light. And because of accelerating expansion, that distance is much smaller. Only about 16 billion light years, which means there are galaxies we can see now that we could never reach, even if we left today at light speed. The space between us and them is expanding too fast. We're watching them recede beyond our grasp. Permanent cosmic castaways. We can see them, but we can never touch them, never visit them, never know what's happening there in real time. It's bittersweet, isn't it? The universe shows us wonders we can never reach, dangles them in front of us like a cosmic tease. But here's what's beautiful about it. We can still learn from them. We can still study their light, analyze their spectra, understand their composition, their motion, their history,